So we're going to be talking about two things which we can't ignore in our designs. If we do, we will have our MOSFET heating up and wasting power. The first one will be the slow gate voltage ramp, and then we'll talk about the gate charge. The slow gate voltage ramp is gotten when we gradually increase or decrease the voltage at the gate of the transistor. Now for this case, I have one channel of my oscilloscope here taking the reading from the gate of the transistor, the MOSFET. I also have the second channel here taking the reading of the drain of the transistor. Now if we look at my oscilloscope, we'll see the first channel is on the screen here. So this channel shows us the pulse width modulated signal at the gate of the MOSFET. Alright, while our second channel will be showing us the voltage of the drain of the MOSFET. Okay, so if we zoom in to this a little, okay, we'll see what this wave really is like. Alright, so at this point we have the voltage at the drain high, which means our MOSFET is turned off. Okay, while the switch on happens around here, and at this point our MOSFET is turned on. Okay, so we can say right here that our MOSFET is at the cutoff region, right, where it's completely turned off, and at this point it's at the saturated region where it's completely turned on. This is the area where it switches on. So around this place, from here to this part, would be our MOSFET within the linear region, okay, where it's not completely on or completely off. So if we look at the gate voltage, we would see that we have a ramp. Alright, this ramp is what we're talking about now. So if you look at it closely, we see I'm trying to zoom out now. This is the signal, the pulse width modulated signal for our gate. If we zoom in, we see it's not a rapid rise, it's a slow rise, So we have a ramp here. This voltage ramp can determine the amount of losses we would have, both switching losses and conduction losses. Now, the slow gate voltage ramp has its advantages and disadvantages. It's the designer's responsibility to locate the balance suitable for his application. So let's briefly consider these factors. For advantages, a slow gate voltage ramp reduces switching loss due to the gradual voltage changes compared to a rapid change. Next, I can say it reduces EMI generated from fast switching of the MOSFET. Alright, so when I say EMI, I mean electromagnetic interference. Okay, so next, it prevents current inrush at startup, okay, especially when we are dealing with capacitive loads. Alright, so it also reduces electrical stress on the MOSFET, which helps us with lifespan, helps your MOSFET live longer in the circuit. Now let's go to the disadvantages. Okay, so of course we now know the advantages of a slow ramp, so I will still start by mentioning losses. Alright, for disadvantages. Okay, so because if your ramp is not steep enough, the MOSFET will spend more time in the linear region. And remember, in the linear region we mean the region where your MOSFET is not fully on or fully off. So the gate to source acts like a resistor is between them, and they definitely dissipate heat. And so the MOSFET is not expected to stay in the linear region for too long, alright, when it's used as a switch. Okay, because it even reduces the overall efficiency, because you have more power wasted. I mean, if the drain to source acts like it has a resistor between them, you're going to have conduction losses that will come from the current flowing through the drain and the source multiplied by the voltage across it. So that's the loss that will be generated. So you see, it's important that the MOSFET, when switching, is completely on or completely off, so we can avoid losing heat by incomplete switching. So what I have just said for the slow gate ramp is that we don't want to operate our MOSFET within this region, this linear region. So we need to move as fast as possible from this point to this point. But then remember, slowing this down, slowing our transition, also has advantages, but it also has disadvantages. So it's like I said previously, it's the designer's responsibility to pick his balance. Okay, now if you go too much over any of the edges, if you go towards any of the extreme, you would have issues. So you find the proper balance where your circuit will perform perfectly. The next thing I want to talk about is the gate charge. Okay, that's the second thing. Now MOSFETs don't heat up due to conduction losses alone, but they also heat up due to switching losses. When we have a PWM send signals to the gate, the MOSFET turns on and off rapidly, and within this period the gate capacitance must be charged and discharged every cycle. And during this period, the power loss, of course, is the gate charge times the gate to source voltage times the frequency of the switching. This energy is dissipated in the driver as heat, but then even if it is dissipated in the driver, it goes a long way to determine the switching speed of the MOSFET. And we already know that when our switching is low, we have energy loss because it spends longer time in the linear region. Now, that's one part of how our gate charge would affect our circuit. Now, secondly, there's a concept of the Miller plateau. If you look at the waveform of the gate on our screen here, we will see that during switching, we'll see a flat horizontal region here. Let me zoom in a little bit. Okay, so of course it's very clear now. We can see we have a flat horizontal region. What happens is pre-threshold phase of the gate voltage. By that I mean when this gate voltage hasn't risen above the threshold. Of course, you know, if you look at the screen, you'll see the gate voltage begins to rise here, but the MOSFET doesn't switch on. It switches on about somewhere here. Okay, you can see this gate starts to rise at this point, but our MOSFET finally switches on somewhere about here. Okay, let's say somewhere about here. All right, so between here and here we have voltage at the gate, but it is below the threshold voltage, and so our MOSFET can't come on. So this is the pre-threshold phase. At this pre-threshold phase, the MOSFET is turned off. Most current flowing into the gate flows to charge the gate to source capacitance. All right, because the gate with respect to the source acts as a capacitor. Okay, so once you send voltage to it, a little bit of current flows into the gate and it gets to a point where it stops, just like you have with the capacitor. So the gate with respect to the source acts as a capacitor. So between when the voltage shows up at the gate and when it gets to the threshold, current is going to be drawn, but it's going to be used to charge the gate source capacitance. So just as the MOSFET starts to turn on, the drain to source voltage drops rapidly. We can see that rapid fall of the drain to source voltage. Now this is, remember I said this is the drain voltage with respect to our source, okay, while this is the gate voltage. So we see that rapid fall of the drain to source voltage, and our gate current now diverts to charge the gate to drain. And once this happens, our gate current now, instead of just charging the gate to source, it now flows to charge the gate to drain capacitance. So we have another capacitance showing up now between the gate and the drain, and so we have current flowing in to charge that capacitance. The gate to source voltage steady, so that's why you see we have this straight line here. Now if you look at the wave, you will see that after our drain to source voltage drops very low, we now have our gate to source voltage continue rising. So we see that steady rise to the top right up until the MOSFET is fully on. And this same thing happens during switch off, and this is what is called the Miller plateau. All right, now why is all this important? This is important because the Miller plateau happens to be the slowest part of the switching period. You can see that it's the slowest part, and during this plateau we have a resistance between the drain and our source, therefore a voltage drop, which would then equate to conduction losses. So how do we control this effect? Alright, first of all, we can use a MOSFET with a low gate to drain charge. So while we're looking at the data sheets of our MOSFETs, we pick MOSFETs that have very low gate to drain charge, and that will help this horizontal line to be shorter. Secondly, we would need very strong drivers to switch quickly. This way we're going to reduce the amount of time, of course, that we'll spend from turn off to turn on. So these are two things we really do need to consider while building our circuits. If we don't take these into considerations, especially when we're dealing with high loads, we would have our MOSFETs misbehave drastically.